take a particle and we move it around in a vertical circle. So this is the center. This particle is attached to the center, let's say by a string. This is not a very good circle, but assume it's a very good circle. There's a string. And let's say I will take the highest point here, let me call it point A, and the lowest point here, let me call it point B, and find out the forces on these particles, because I need to set up the force equation. This is one of the problems kids have. They don't set up the force equation good enough. And then everything goes wrong from there. Okay? So let's look at the situation at the lowest point. When the particle is here, clearly you have mg acting downward. So we are doing what we call the free body diagram, or the force diagram. So mg is downward. And since there is a string at this position, the string obviously is holding this particle with respect to the center. So the string will be stabilizing it from falling down. The string tension would be that. And we also know that the particle is going around in a circle, which means there will be a centripetal force. And the centripetal force will be inward along the direction of the center. So in other words, there will be a centripetal acceleration, if you will, back way too, and we'll call that a centripetal. So therefore, if I want to set up the force equation at point P, at point B, what we would do is we would take, since on the right-hand side of the equation, I would have an upward force, I would take the upward force T minus mg as my left-hand side as mac. So that would be the correct way of setting up the force equation for the system. This is where students have a great deal of trouble, because setting up the force equation requires you to be conceptually very clear about what's happening. So in this case, you can see that the right side, this side, deals with the net force. And the left side deals with all the forces responsible for the net force. Okay, so it's very important that you separate the two. Don't mess it up. Because if you got the right side wrong, you got the whole problem wrong. If you got the left side wrong, you got the whole problem wrong. There's absolutely zero room for error in setting this up. And everything rests on your drawing and understanding the free body diagram, right? Yes? At the end of the day, that's all you got left with if something is going around in a circle, right? That's also a big conceptual point. We have tension, we have weight, we have whatever else, but at the end of the day, if something is going around in a circle, the net force that you'll be dealing with will be the centrifugal. So you have to identify that. That's the reason why the practice and all the immersion is needed. Because it doesn't come to you naturally. It's an acquired skill. Alright? So at this point you can already see what's happening. The tension, which is effective weight, as I captured in the lectures I put on video, is going to be more than mg, right? Because if I take mg to the right side, mg becomes plus, and the tension is what you really feel, and the tension is, if you will, the effective weight of the particle, and that is mg plus ac. In fact, in neat balance at the lowest point, it will feel the heaviest. The highest point, it will feel the lightest. In fact, you can do it yourself. Just take a piece of rock, tie it to a string, and take it around. So at point A, what happens? At point A, what happens is that you have an interesting situation. All the forces are downward. mg is downward, T is downward, and AC is also downward because AC is towards the center. So now what happens is, I should be able to write, as far as the top is concerned, that I have tension downward, so let me call it plus. I have mg downward, let me call it plus, and I have the centripetal acceleration downward, let me give it the same sign, because they're all downward. Everything downward, let's say, is plus. So now we are left with a scenario where you see the tension now becomes m times AC minus G. So in other words, the tension now is much less as it goes in the top, and the tension actually depends upon how fast it's going, because that enters through the centripetal acceleration. Okay? Questions? All right. Some of you are talking. You too. Yes. Don't look at the back. It's you and you. Yes. Unfortunately. So next time I catch you talking, both of you will not get a question. I'm sorry. You want to share around with me? That's what you get. Anybody else I catch talking? I do the very same thing. One more time. I see you guys doing anything together. You do not get a question. Because it is annoying the heck out of me. Alright. So if you don't have any questions, I'm going to move on to some greener territory. Okay? So let me do that. In my video lectures, I had covered a car going around the circular trajectory. So in that problem, be very careful that you understand everything. Because when a car is going around a circular flat road, it's very important you understand that weight acting down and the normal force acting up, they are balanced. So that's no biggie. So let's say my hand is the car, the weight acting down and the normal force acting up, they should balance out, right? That's no biggie. Now what is a biggie is that this thing, as it is negotiating the circle, it is not slipping off in this direction. That's what you want to make sure. Indeed, when you take a turn on a flat, icy road, most roads are not really flat actually. But if you were to take a turn on a flat, icy road, you should know, living in Buffalo, what happens to you, right? You go outward, isn't it? Right, you go outward. So, to stabilize, being able to stay on a flat, icy road and make a circular track, in the radial direction, you don't want to move out, right? You don't want to move. So you should make use of friction to be able to stay on track. So since you have a tendency to move out, we know that from intuition. Which way would friction be? Inward. It's very important. Don't screw this up. Screwing up friction is like a dharma. Everybody does it most of the time, unless you are careful. It's very non-intuitive at some level. So in this case, you're going to slip out. But you don't want to slip out, and to stabilize that, you want the friction to be acting inward, to hold you in. So this friction, which is going to be normal force times a mu, right? That's what friction is. You don't know that, you're in deep shit. Normal force times a mu, that's what friction is. That must be equal to the centripetal force. So that's your equation of motion, that's it. So when you take a turn on a flat road, flat icy road, it's the friction that saves you, and normal force times mu, which is the friction force, is equal to mv squared over r. Now mind you, what mu is that? Let's see how many of you know. Huh? No. It has to be static because we do not want to slip out here. You put kinetic in the exam, I'm going to just skin you alive. Because that is exactly not the point. That is what I told in my lecture, and you didn't listen to it. At least not listen carefully enough. So do not screw this up, okay? What happens when you have a bank road? That's a very tricky problem. So let me just quickly review that. So if you are going on a bank road, most roads have some banking when you take a turn. The road kind of goes like this, if you have a notice. That's called banking, right? All the roads out here. Otherwise, there will be so many accidents you wouldn't even know. If you go to something like Daytona race course or the Indy race course, what you find is that the race course is like that. You won't be able to stand there, you let fall. So it's heavily banked. Why? It has to be heavily banked if it's going to support cars going at 200 miles an hour are flying off, and they fly off still, right? So what it is that this is the way the car would be going around in a circular trajectory. So mg would be like that, but now the normal force, because of this banking, would be that. Alright? Now see what I do. This is really weird. So this angle, let's say, is theta. If this angle is theta, here I will not be drawing my axes the same way I draw for a typical inclined plane problem. It is done differently. That's the point. That's the reason why this problem is important. That's the reason why people screw it up. So I will draw my axes in such a way that one axis precisely counteracts the mg, and the other axis would be inward, radial. Why? Because I'm ultimately going around a circle. So I need my centripetal force to be incorporated into the problem, which means being able to do this radial business is very important. So you see, if this is m, if this is theta, this is theta. Here also you have to be very careful. This angle is theta, which means n cosine of theta would be this one, the upward one, and this would be mg. And then n sine of theta, which would be this piece of n, that would be equal to mv squared over r, where r is this radius of the circle that is negotiable. So now you see, you can immediately make use of these two equations, 1 and 2. Now, whenever you have a sine, n sine theta something, n cosine theta something, you should have the irresistible urge to divide one by the other. But put the sine on the top, you get a tan. So you see, if I do n sine theta divided by n cosine theta, that would be n sine theta would be mv squared over r. That's this equation divided by. Now I'm just dividing one equation by the other equation, weird as it may be, and that immediately gives me my friend tan theta, which is v squared over r, and here's a g, and if you work it out, this is v squared over r times 1 over g, which is v squared over rg. That is tan theta. So in other words, this banking angle here, ties in with g, ties in with how large r is, and ties in with how fast the car is going. So if you're going at 200 miles an hour, convert it to meters per second, then you know what angle you want to be able to sustain the whole problem. G you can't change, but R you can control. So that's how you design at the crudest level one of these racers. Questions? Yes.
How do you make to answer G?
So this and this are perpendicular, right? This is the normal force. It has to be perpendicular to the surface, and basically this and the horizontal here is perpendicular. I didn't draw the horizontal. So if this is perpendicular to that, and that is perpendicular to this, if this is there, isn't that perpendicular?
Oh, yes.
That's why I have my finger trick. Any other questions? This is an important problem. We always ask about this problem in some exam or another. Alright. Let's do something else. Change gears. Have some fun. So let me tell you a story. We did the vertical circle, but when the earth goes around the sun, or the moon goes around the earth, we don't have a string attached between these two bodies, right? So what's there between these two bodies? Come on, be brave. Gravity. It has to be gravity, right? So let's look at this a little bit. Let's track back. So in other words, if you have a star, let's say sun of course is a star, It's a very ordinary star by every measure. And then you have, let's say, some planet, let's say Earth going around the sun. Okay? This is my picture. So this is the star and this is the planet. Now the same thing applies when you have when you use your cell phones. The data is bounced off what? Satellite. And the satellite is pretty high up. Satellite is actually sitting in space, pretty high up. And in fact, the satellite is orbiting the Earth, so if you take into account all of these things. In fact, more. Do you know how many of you use GPS? No wonder so many people are lost. Everybody is not using GPS. So with GPS, you want to make sure that you get the right coordinates to go where you want to go, right? In fact, if GPS got the wrong coordinates, you'll be pretty pissed off, isn't it? Do you know that to get the right GPS information, you actually use something that you almost never dreamt of is used? That is Einstein's theory of general relativity. If Einstein didn't have general relativity, your GPS will take you to the wrong place, my friend. Because those relativistic corrections that are inserted because of Einstein's general theory of relativity, which is not the easiest thing for any physicist to understand at any time, you'll be in the wrong place. Those corrections matter. Those corrections matter. The amount of rainfall that was needed in California some years ago, this was on TV like a year and a half ago, because California had its biggest drought in like a couple of decades. The rainfall that was needed in California, that was measured. You were told on TV that California needs, God knows how many, 60 inches of rain or something to just come out of the hole that it has created for itself, or nature has created for California. Southern California in particular. It turns out that to get that number, you needed general relativity, because those numbers were measured by looking at the color of the surface of the Earth, that part of Southern California, from space. And they needed 2 satellites to triangulate and get correct information about the color and general relativity corrections as the satellites were going around them. So anyway, the point is that you need a hell of a lot of physics that you probably are not aware of. I certainly am not aware of all the time. So at any rate, let's now go back to one interesting character. You can look up Tycho Brahe. Tycho Brahe lived in the 1500s, like 1400s. Tycho Brahe came after Nicholas Copernicus. Copernicus was a very interesting character, and Copernicus was one of the first guys, certainly in the Western scientific community, to point out that we have a heliocentric system. In other words, we have the sun in the center, and everything goes around the sun. That in those days was blasphemous. It was enough to get your head cut off. So you should be lucky that we are living in better times, right? So what Tycho Brahe did was he did something quite interesting. He did a great deal of measurements, looking at the skies with his telescope. He was a very accomplished astronomer. And he was also actually, he belonged to the Dutch Royal, so he was quite an interesting guy. Anyway, the mean distance of planet from the sun, our sun that is, he measured, and we would report this distance r in millions of kilometers. Okay? So for Mercury, which is the planet nearest to the sun, it takes Mercury is 57.9 times 10 to the 6 kilometers. It's about 58 million kilometers from the sun. How far is Earth from the sun? Do you guys know? No clue?
8 light minutes.
Huh?
Approximately 8 light minutes.
8 light minutes is correct, but light minutes is a slightly different unit. I'll give you, it's about 93 million miles, about 150 million kilometers. In fact, we will become extinct by the time this distance comes a little less than what it is because Earth will eventually go inside the sun. Two things will happen. Earth's orbit around the sun will shrink, and the sun, as the sun is getting old, is getting fatter. So the sun will come closer to us, and eventually we'll be inside the sun. Now, Jupiter, which is the largest planet we have, the gas giant, 778 million kilometers, and Pluto, which is no longer even a planet in the Kuiper belt, is 5,890 million kilometers. So these are the distances. So the period to go around the sun, that could be measured in those days. I don't think Pluto was actually measured by Brahe, but anyway, I'm throwing the data. Mercury is pretty fast. It's 0.241 per year. Okay, this is in a year, Earth year time. So in other words, it's about a quarter of a year, which is 1/4 of 12 months, which is about 3 months, slightly shy of three months is a Mercury's year. Earth we know is a year, 1.00. For Jupiter, it takes almost 12 years to go around the sun. And for Pluto, it takes a whopping 248 years to go around the sun once. That's a Pluto's year. So by Pluto standards, that'll be a few months old. All right. Now you see, from there, you can calculate omega squared r. Remember, omega squared r is a very important quantity because omega squared r is basically v squared over r. We discussed this earlier. Centripetal force, centripetal acceleration. So if you take omega squared r, the units will come out 10 to the 9 kilometers per year squared. Funny unit, but it's something that's convenient. That's okay. So this turns out that this is 39.4 times 10 to the 9. That's omega squared r here. For Earth, it's 5.92. So these numbers are a little weird. For Jupiter, it's 0.217 because it's far away. So r actually is quite large. And for Pluto, it's even less, 0.0038. Okay? All right? So that's what you got. This is what Tycho Brahe had, sort of this kind of data. Again, Brahe may not have Pluto. I don't think Brahe had Pluto. But if you were to plot, the centripetal acceleration against r, so this is the centripetal acceleration omega squared r versus r. Or you can even plot it as versus r squared. You find that this plot kind of goes down like that, like a hyperbola. You can plot it in a variety of different ways. You can, if you are familiar with the logarithmic plots, you can make a log of this and log of that, and this will look like a straight line. Or you can plot it this way, or you can plot it as 1 over r squared, in which case it will go like that. So anyway, this is what Brahe did. Actually, most of Brahe's processing was done by his assistant, who is Johannes Kepler, whose name you may have heard. So Kepler eventually came up with the point that the centripetal force involved, which is due to gravity, must decay out as 1 over r squared. So in other words, the upshot of the study was that omega squared is proportional to 1 over r. If you think about it, it's pretty remarkable. It's pretty remarkable that this is a centripetal acceleration. If I put the mass in here, right, it becomes a centripetal force. So it's telling us that the force that is being fed by these planets as they're going around the star, in this case the sun, varies with distance as 1 over r squared. It is not 1 over r to the power 1.99 It is not 1 over r to the power 2.1 or 2.01. It is as precisely as we know, even today, as precisely as we know, it's precisely 1 over r to the power 2. Why nature likes 2, we don't know. But this is the law of nature, and in our universe, we have to live with it. So, the long and short of it is that later Newton formulated, based upon all this work, what we call Newton's law of universal gravity. Okay? So Newton's law of universal gravity basically tells us that if you have two masses, suppose you have a mass small m here, and you have some other mass, let's say big M here, at some distance apart, let's say the distance is small r, then the force between these two guys, so this mass will attract that mass. In other words, as far as this mass, big mass is concerned, it's going to feel a pull towards the small mass m. And as far as the small mass is concerned, it's going to feel the same pull in the opposite direction towards the big mass m. That's how gravity works. I pull you, you pull me. So this force, gravitational force, turns out to depend on both the masses, the small mass and the large mass. We already know it depends upon r squared, the distance squared. And there is a universal constant of gravity that comes in. This universal constant of gravity, by the way, was measured at a much later point in time. There are some famous experiments that were done, Cavendish experiments and so on, that you can read about if you're interested. But this g was very hard to measure, because g is a very, very small number. And why is that? Because gravity is a very weak force. So just to give you a sense of that, I don't think our brain is designed really to feel gravity in a serious way at the small scale. So g is 6.67 times 10 to the minus 11 in SI units, okay? So let's get the units right. So we know that this is in newtons. We know that this is going to be in kilograms squared over meters squared, right? So therefore G, the correct unit for G would be Newton meter squared over kilogram. That is the correct unit. So let's see how weak this force is. Suppose both of these masses are 1 kilogram. That's about what, 2 pounds? 2.2 pounds? So that's something that's palpable, right? We can take a bunch of fruits, let's say. You can take a watermelon, relatively modest sized watermelon, 2 watermelons in your 2 hands. That will be about, let's say, 1 kilogram or 2.2 pounds. Just go to the grocery store and do this. Right? People will think you're crazy, but what the hell? If we do this experiment in the grocery store, so then you can set small n equal to big N. So say that's roughly 1 kilogram, and you hold them about 3 feet apart, right? So let's say your distance r is 1 meter. Then what it's telling us is that the force involved between the 2 watermelons would be approximately 6.67 times 10 to the minus 11 Newton. That's what it's telling us. It's going to be G, right? That's an extremely tiny force, and we can't feel it. So our brain, our sensory organs are not really designed to feel something that fine scale. Just to give you a hang of a Newton. Have you ever pressed a doorbell? Do you know what a doorbell is? Alright. So when you press the doorbell, you press the damn thing, right? So the force that you apply when you press a doorbell is of the order of close to half a Newton or so. So we can feel relatively small forces, maybe, I don't know, maybe 1,000th of a Newton, maybe a little less than 1,000th of a Newton. So if, at the very best, I don't know if you can really feel it easily, anything less than 1,000th of a Newton. Maybe a little less, but not much less. But this, as you can see, is a millionth of a million, right? So if we make this into 0.6, it's a million is 10 to the minus 6 here, a million. So this is 10 to the minus 6, 10 to the minus 6. It's roughly a millionth of a million. That's how small gravity is. But gravity, while it's very small at short range, it is an enormous force at longer range. In fact, the entire universe is what it is now. Your night sky is ruled by primarily one force at the base level, and that's just gravity. Look up in the sky, and essentially you see what gravity has done. All those things that you see, most of the lights that you see are actually stars, just like our sun. And those are the visible stars. And that's a teeny tiny fraction of what the universe is. In that scale, gravity is the king. So gravity is one of the universal forces that you learn about. Alright, so now that we know that, let me just go back to my problem of Earth going around the sun, let's say. And I can write Gm m over r squared equal to m, let's say this is Earth, this is sun, and v squared over r. Alright? So this is the centripetal force, because the centripetal force is what's involved, and the centripetal force comes around because of gravity. Right? We agreed sort of that must be happening. So now what I can do is I can cancel out ends here, because that m is not 0. I can also get rid of one of the r's. I can divide both sides of the denominators by an r. So now I'm left with Gm. So I can immediately compute an expression for v, the speed, and this v would be Gm over r square root. Right? Because v squared is Gm over r. That's what v still. So v would be square root of Gm over r. And since we are talking speed, we don't really care about the sign at this point. The speed at least is things. So, just for the sake of convenience, let me also write 1 over v, and that would be r over Gm. One implies the other, so that's what I mean. Yeah.
What unit would you use for speed in this case?
Anything that is convenient. I mean, because for the Earth, we normally we use kilometers per second, meters per second. It doesn't have to be a fundamental unit, because when you go to astrophysical scales or even planetary scales, the speeds are large. So we use appropriate units like we discussed in the previous. But of course, I mean, at the end of the day, when we are doing our calculation, we want to stick to something like an SI system of units and then convert them back out to wherever we want. Alright, so now let's look at the period, because the period is very interesting. We know that the speed with which this thing is going around should be 2 pi r, which is the distance traveled over the time period t, right? We know that from our baby days. We have done that a while ago. We forgot that shame on you. So now you see, t is 2 pi r over v. So now you see something interesting happen, because I've already written 1 over v here. That will be 2 pi r times r over Gm, right? Any objections? So what does this tell us? This tells us the following. It tells us that the t, the period associated with going around the star, let's forget about the constant, is proportional. There are 2 r's here. There is an r times root r, which is root r means r to the half. So that means it's proportional to r to the 1 plus half is 3 half. So t is proportional to r to the 3 half. And if I square both sides, it means t squared is proportional to r cubed. This, by the way, is one of the very important laws of Kepler. This was experimentally observationally found. And Newton's universal law of gravitation gave us the structure needed to be able to explain what was seen by Tycho Brahe and Johannes Kepler, as well as explanations of the work done by Nicholas Copernicus earlier. So if you were to transport yourself back to sometime around late 1600s, these were earth-shattering discoveries because we were able to understand for the first time, A, that sun was in the center, number one. Number two, given that sun was in the center, all the planets were going around the sun, and even as far as moon going around the earth is concerned, that's there too, and so on and so forth. And the period associated with going around, p squared, is proportional to the distance r cubed. Now, one of the things I should tell you is that, to a very large degree, these orbits are not actually circular. What are these orbits like? Elliptical. Our orbits are elliptical. But that said, a circle is a special case of an ellipse. Okay? So in an ellipse is like that. In an ellipse we have two axes. This is called the major axis because this is the longer flattened part of it, and this is called the minor axis. Difference between an ellipse and a circle is that in an ellipse, the major axis doesn't have to equal the minor axis. In fact, they are usually unequal. In a circle, the two are the same. If you make the major axis equal to the minor axis, you get a circle. So a circle, therefore, is a special case of an ellipse. So what we have done is we have derived Kepler's laws for the special case of a circular orbit. Now, when you do it for the elliptical orbit, which is slightly non-trivial extension of this work, you have to be a little bit more careful, a little bit more nuanced, but the same laws come out. So I won't go there because it is not necessary to go there. But we have derived it for the special case of the circular trajectory. All right. Any questions? Okay. So now we'll move on to something which is quite loaded, and this requires a fair amount of absorption from your end. I'll start very simple. I want to introduce the concept of work done, because the concept of work done in physics is a very delicate and technical concept. So work done at some level, from a purely scientific sense, work done has nothing to do with yours having done this and that all day and getting tired. While that is indeed a form of work done, that work done is far more complex than what we mean by physics work done. Physics work done is more delicate and nuanced. So in physics, let's say, I want to push this thing. And you know what's going to happen. I won't be able to push it. Right? So I do this all day and shore up all my strength. I eat 200 eggs. I'll die of a heart attack. I won't be able to push it. So in spite of all that stuff I've done, my work done will be precisely equal to 0. That's a bummer, because it doesn't measure how much energy I expended. Right? So in physics, the definition and concept of work done is very special and technical. Why is it 0? It is 0 because at the end of the day, the table hasn't displaced itself. That's why it's 0. Alright? So if there is no displacement, you have 0 work done. So how is work done? So let us say, now I get lucky, and I apply a force and move something from point A to point B. And let us say this distance that I have covered is, or this displacement rather, that way, right? Because I have taken it from A to B, is xAB. And it's actually a vector, right? And since I'm applying a force in the same direction, let's say, the force is also obviously a vector. So work done, very weird. Work done in going from A to B, alright, is defined as, which is what these 3 signs mean, it's defined as, that's the law, we make the law, as in this case force, right, times XAB, which is the displacement. Both are vectors, but now we are multiplying the vectors. We have thus far not done vector multiplication, we have only done vector addition. So now for the first time, I'm uttering the words vector multiply. So we are actually multiplying the vectors. But this multiplication is a very weird form of multiplication. Actually, vector multiplication can be of two kinds. One is when you multiply two vectors and the resultant, the product is a vector, which should make sense. But this is a weird case, where we multiply two vectors, but the product is a scalar, it's not a vector. Alright? So this guy, work done, is a scalar. Work done doesn't care if you're going to the right or left. Work done only cares about this product. It can be plus or minus, but it doesn't have any directionality. So this is a scalar, but these two are vectors. And when vectors are multiplied and give you a scalar, that product is written with this dot. This is not a normal multiplication sign. This is a name for it. Very boring name. It's called a dot. It's a dot product, okay? This kind of product is called a dot product. What does a dot product mean? A dot product means something very simple. Suppose I'm so stupid that instead of applying the force in that direction, I want to apply the force in this direction. So I want to apply the force like this, I want to displace the thing like that. So this is my XAB, and this is my force. Alright? So suppose, because of my stability, I have invoked an angle theta between the two vectors. So now what happens, you see, is because it is a dot product, WAB defined as F dot XAB, I still write the same thing, but what it means is that it means the magnitude of F, means the magnitude of the displacement XAB, and it means you have to also multiply by cosine of this angle theta. Alright? Now you see the moment you have introduced this cosine, you have allowed for the possibility that theta can be 180 degrees. So in other words, I may be going in this direction, but the force may be in the opposite direction. When does that happen? You know that. I'm going in this direction, the force is in the opposite direction. What force would that be? Friction. Friction never helps. Friction always messes things up. So therefore, you see, friction, what happens is that the force and the displacement direction would often come out in opposite direction. Most of the time. Which means theta would be 180 degrees. What is cos of 180? I showed you guys how to do cos A plus B. What is cos of 180? What is cos of 0? There was a mumbling. Should be brave. Huh? Negative 1. So cos of 180 is negative 1. So if there are two forces at opposition, you get a minus sign. That minus sign comes from the thing. Okay? So this is the basic idea of work done. Now work done is very, very weird. So let me first give you what this work done can do for us, which is why it's interesting. We are now heading up to one of the most important theorems that I'll prove for you. This is a very handy theorem. You'll be using it a lot. So, I've already told you that work done in going from A to B is some kind of a force times some kind of a distance. Let me simplify instead of writing A to B and all that jazz in a big way. Let me say the distance that involved here is a small distance, or displacement, is a small displacement. So I call it delta x instead of x. And because it's a small displacement, I can call this delta WAB. So when I write delta WAB, or delta x, physically what I mean is that these are small quantities. That's what I mean. So that big delta is not being multiplied with things. That big delta is a symbol that says that this is a small quantity. Alright? So, I know that Newton already told us that I can write, and let me simplify things even further. Let me just say that we know both are in the same direction and so on and so forth for now, and so I don't even have to carry the load of doing vectors because theta itself here is 0, so cos of theta is 1, which means I can write things like this. Alright? Cool? Okay. So I can write this force as ma, right? Because Newton's law has told us that force is mass times itself. In fact, if there is no mass, there is no force, as far as we are concerned. As far as Newton is concerned. That doesn't mean it's necessarily always true, but that is true for our purposes. So I should be able to write delta WAV is ma times delta x. Now let us see, make a simplifying assumption. And the simplifying assumption I'm going to make is that let acceleration A for now be constant. So in other words, the force is such that the acceleration is constant. What force would that be? Where acceleration is constant that you love so much? Come on. Don't overthink it. Huh? mg. Why are you bumming? mg. You fall. Acceleration is constant g, right? So that's okay. Now we can use some kinematic relations because I know that v final squared is v initial squared, or v0 squared if you will, plus twice acceleration times distance traveled. I call it delta x. I should be able to write this, right? This is our old friend. You should be happy to see this guy. So that would mean, this means implies, I should be able to write 2a times delta x is v final squared minus v0 squared, right? Any objections? Am I misleading you intentionally? I could. I tried to do it sometimes. If I'm not, then I'm being too nice. Alright, so now I can write acceleration as v final squared minus v0 squared. My 2 gets a little squashed sometimes. You've got to take care of my 2. 2 delta x. I put delta x in the bracket because it's a small quantity. That's what delta x means. It's not delta times x. Don't screw that up. Okay? So, alright. So now, you see I have found an expression for acceleration only for the case when the acceleration is constant. If it were not a constant, I would have had problems. So now you see I should be able to write my work energy theorem, this thing here that I'm putting up to. Delta WAV is mass times v final squared minus v0 squared divided by 2 delta x. Alright, so this is my MA times delta x. So happily the delta x's will go. So what I'm left with is delta WAV is 1/2, which by the way goes like this, 1/2 m times v final squared, which is actually the velocity at b, because it's going from A to B, minus 1/2 v initial squared, or this. So I can dress it up now. I can dress it up, and I can say that the amount of work done in this process, whatever it is we're describing, is 1/2 mv final squared minus 1/2 mv0 squared or v initial squared. So, does anyone know what this quantity is? If I write half mv squared, do you know what that quantity is? That one, yes. Yeah, that quantity is very important for us actually. In fact, that quantity is a very fundamental quantity that we use in physics. It's called kinetic energy. Kinetic energy is the energy by virtue of motion. Do I have kinetic energy right now? Great. Do I have kinetic energy right now? Yes. Okay. So now you see that WW I can write in short form as kinetic energy final minus kinetic energy initial. This particular statement, that work done is kinetic energy final minus kinetic energy initial, is a very important theorem. It's called the work energy theorem. And I'll tell you why it's important. The work energy theorem is important because it will take us to places we cannot go without it in terms of understanding nature. For one thing, work energy theorem is a great way of estimating energy loss due to friction. It's a great way of getting it. Because all we need to care about is the force and the displacement involved. Just like I gave you the example, right? I'm walking this way, friction is the opposite way, so therefore friction is opposing my motion. So I can calculate the work done by friction. And in this case it will turn out that the work done by friction will relate to my final kinetic energy, which should be less than my initial kinetic energy. If I'm sliding, let's say, on a board or something, or if I'm, let's say, this is not a good example. Let me push this. So, I'll get this out, just observe it. So now you see what happened was I gave it an initial velocity, and this initial velocity went away and you can see the final velocity was 0. Initial velocity was whatever I gave it, let's say half a meter per second. Right? And friction was opposing the motion. So therefore, the work done by friction in this case would be the displacement, which would be that much, times the friction, which would be that way. So there'll be a minus sign because it's a cos 180. So friction times displacement is some negative number, right? That's my work done. So what this theorem tells us is that this work done is equal to the initial kinetic energy. So kinetic energy is when it started to move and the final kinetic energy. That's it. That difference. So final kinetic energy minus initial kinetic energy would be a negative quantity because this is larger than that. So therefore, the work done by friction can be estimated using work energy theorem. It's a trivial thing to do, it's very, very handy, and in case you don't know, you'll be working probably till you are 70 years old, right? If you think you'll be retiring early, let me know how. I don't think I'll be retiring at 70. So at any rate, so suppose you work till 17 or 20 years, 50 years you work. For 50 years you work. Let's say you make enough money that at the end of the day you have, let's say you have $3 million. You'll be rich too. Do you realize that you could have made a hell of a lot more had you not been paying for friction? Everything you do, you pay for friction. The cost of overcoming frictional forces in terms of US GDP, gross domestic product, is 1/3 of it. That's a third of a few trillion bucks, or a few hundred trillion bucks, whatever that is. But that's how much we pay for friction. In fact, you pay your electricity bill because of frictional losses. You pay for gas because of frictional losses. You pay for your clothing because you're primarily paying for labor and frictional losses. You name it. Every damn thing you do, you'll be paying for friction. You are doomed. You better understand work energy theorem to beat friction. Alright, with that I'll stop now. Let's go to the quiz.